Guys, so today we're going to look at a practice problem together. So what you'll see on your screen is the hydrogen atom according to what's called the Bohr model. So there's a couple different atoms or elements where they've actually found some specific information about the first couple of energy levels, and they were named after the scientist that was able to find that. And what this representation refers to is where the electrons can be around the nucleus of the atom. So you can kind of think of these, if we think back to our planetary model, as each orbit around the nucleus of the atom. What you'll notice is that the ground state, so n equals 1, the ground state is the closest to the nucleus that it could be. It's actually a negative value, negative 2.179 times 10 to the negative 18th joules. And this is because what it represents is that it's showing that it's stuck in the atom. So in order for an electron that's in the ground state at n equals 1, in order for it to completely leave the atom, it would need a minimum of 2.17 times 10 to the negative 18th joules of energy to completely leave. And that negative is just representing that it's stuck inside the atom. Then we've got our n equals 2, negative 0.545 times 10 to the negative 18th joules, and so on and so forth. We're just going to look at the first 4 states that the electron can be in. So the first question on this is a photon of light absorbed or emitted when an electron goes from the level of n equals 4 to n equals 2? So is an electron absorbed or emitted as it travels from, n equals 4 to the n equals 3 level or state? So if the electron is moving from a higher energy level or an excited state, so anything that's not the ground state is an excited state. If it's moving from an excited state to a lower level or lower excited state, it has to emit energy, has to give off energy. Anytime the electron moves from a low state to a high state, it has to absorb energy. So an electron moving from n equals 4 to n equals 3 would emit energy, would give off energy. So now the question asks, what is the energy of the photon in electron volts that is emitted or absorbed when the electron moves? Well, before we get to that question, actually, I want to show you guys something really quick. So yesterday we talked about how an electron can get from a higher state to a lower state and the different paths that it can take. So I want you to take a moment or two, and if we have an electron in the n equals 4 state, how many different paths can it take to get back to the ground state? The easiest way to go about this is to draw it. So I'm going to sketch it on a piece of paper. We know that we're starting on the n equals 4 state. So the first thing that my electron could do could be to jump from the n equals 4 to the n equals 1. So just like I showed you guys yesterday, that's an arrow from the n equals 4 to the n equals 1. Now just for fun, if we wanted to know how much energy that is, we would take the most energy, the energy of the ground state, 2.179, and we would subtract the energy of the n equals 4 state, 0.136. So, oops. And that moves from the n equals 4 to the n equals 1 state would emit a photon of energy, 2.043 times 10 to the negative 18th joules. But not that important. Now let's look at the other paths that my electron can take to get to from n equals 4 to n equals 1. My electron could also go from 4 to 3, 3 to 2, 2 to 1. My electron can go 4 to 3 and 3 to 1. My electron can go 4 to 2 and 2 to 1. And I think we got them all. So if we look at these, we've drawn 8 separate arrows. The arrows make up 8 different energy emissions. But if we look closely, there's at least 2 here that happen twice, right? So we drew the n equals 4, the n equals 4 path twice. And we also drew, let me do it in a different color. We drew the 2 to 1 path twice. Hopefully you can see that. My lighting's not very good today. Oop. Make it straight. There we go. So we don't double count, right? So we would say for this, if we don't double count all the arrows, that there are 6 photons of energy. I didn't give myself enough room. 6 photons of energy, photons of light rather, that could be emitted for the electron to move from the n equals 4 to the n equals 1 or ground state. Okay, cool. Okay, now let's go back to this question on the screen. What is the energy of the photon in electron volts that is emitted or absorbed when the electron moves from the n equals 4 to the n equals 3 energy level? And just make sure you pay attention. The energy scale on this model is units of 10 to the negative 18th joules. So what we would look at is we're looking at from n equals 4 to n equals 3. So the n equals 4 level, so the n equals 4 energy level has 0.136 times 10 to the negative 18th joules. And the n equals 3 has 0.242 times 10 to the negative 18th joules. Notice when I'm saying these values, I'm ignoring the negative, because the negative simply is telling me that the electron is still stuck really close or inside the atom, right? Stuck close to the nucleus or inside the atom. So if I want to find the energy of the photon that is emitted from the n equals 4 to the n equals 3 state, I simply have to find the difference between those two values. So the difference between those, the energy that would be emitted is 0.106 times 10 to the negative 18th joules. 0.106 times 10 to the negative 18th joules. But we don't want the answer in joules. We want the answer in electron volts. So we simply need to convert. I've provided how many joules are in 1 electron volt. So if I'm changing my units from joules to electron volts, I would need to divide by the number of joules in 1 electron volt. So in 1 electron volt, there's 1.6 times 10 to the negative 19th joules. So I would take my value, 0.106 times 10 to the negative 18th, and I would divide that by 1 times 10 to the negative 19th joules. And I would find that the energy in electron volts for the photon that is emitted is 1.6 electron volts. So I showed my first calculation in red and then my conversion in green. Okay, let's move on. So what is the wavelength in nanometers of the photon that is emitted or absorbed? The other day, you guys determined a relationship between energy, Planck's constant, the speed of light, and wavelength. And that relationship was E equals h times the speed of light over the wavelength. So we know the energy of the photon. It was 1.06. We're using electron volts, so we want to use Planck's constant in electron volts. So if we look back at all of our equations and things like that, Planck's constant in electron volt seconds is 4.14 times 10 to the negative 15th. So that's the value that we'll be using. 10 to the negative 15th. And then we always know C, 3 times 10 to the 8th. and we would solve for wavelength. So some rearranging, some algebra, algebra cadabra. We find that the wavelength of this emitted photon is 1.17 times 10 to the negative 6 meters. We wanted that in nanometers just for fun, 1,171.7 nanometers. And I just had to convert. So determine the following using the same energy level of the hydrogen atom. So our same image before, that guy right there. So if you want to take a quick screenshot. Now we want to calculate the wavelength of light needed to excite an electron from the n equals 1 to the n equals 4. So excite just means it has to absorb energy. So first we look at the model of the atom, and we see that at n equals 1, it would need 2.179 times 10 to the negative 18th joules to leave. And at n equals 4, it would need 0.136 times 10 to the negative 18th. So to find the energy absorbed, we find the difference between those two values. And we would find that the energy absorbed from n equals 1 to 4 is 2.043 times 10 to the negative 18th joules. So if I want to calculate the wavelength, I can use the same equation that I used before. E equals Planck's constant C over the wavelength. Here's what we have so far. And it's totally up to you. You can leave energy in joules. You would just need to use the Planck's constant that is in joule seconds. Or you can convert to electron volts and use the same number as before. So if I set this up, 2.043 times 10 to the negative 18th, I'm just going to leave it in joules, equals, and I'll use Planck's constant in joule seconds, 6.63 times 10 to the negative 34th, times the speed of light, over the wavelength. So again, just some algebra. We would find that the wavelength is about 9.7 times 10 to, you can see it, negative 8 meters. This particular problem wants the value in nanometers. So we need to divide by times 10 to the negative 9th, because 1 nanometer is 1 times 10 to the negative 9th meters. And that gives us that the wavelength is 97.36 nanometers. That's just converting from meters to nanometers. So the next question, we actually already answered this. How many different possible photon emissions are there as the electron moves from n equals 4 back to the ground state? So we drew this out at the start of our video, right? We drew the red arrows on our diagram. And we found that we would draw 8 arrows, but since we do not double count things, we only had 6, right? Okay. Consider the bluish-green line in the hydrogen emission spectrum with a wavelength reading of about 490 nanometers. Which electron transition does this correspond to? So this means what level is the electron moving from and to in order to get a wavelength reading of about 490 nanometers. So our step 1, convert from nanometers to meters. So 490 times 10 to the negative 9. Step 2, use the relationship E equals Planck's constant C over wavelength. And I use Planck's constant in joule seconds because my table is in joule seconds. Find the amount of energy that is and figure out which transition it refers to.